Oh shit. Alright, today I've got some pretty short, hopefully, propositions for us today. We're going to go over the fact that convergent sequences are bounded, and then we're going to go over some limit laws. For the first proposition I want to show today, convergent sequences are bounded. We're just going to let AN be a convergent sequence. So since AN converges, it converges to something. So there's some real number that it approaches. So we're going to let epsilon be equal to 1. Why not? We know then that there is some natural number n such that for all n bigger than big N, the distance between AN and A is less than epsilon. That's equal to 1. Okay, so let's draw our thing here. You've got a graph. We got A up here. We got a bunch of ANs. Down here is going to be actually A minus 1. Here's going to be A plus 1. A bunch of terms are maybe all over the place, but then eventually they all get stuck in here. Okay, and that means we're going to take this guy to be our n right here. After this n, since all the terms are stuck in here, they're all below this. And they're also all above this. So eventually all terms are in here. All right, so the ANs starting from big N to infinity is bounded by, we'll call big M equal to, we'll just call it the max of A plus 1, A minus 1. All right, then, moreover, finitely many real numbers are always bounded. Finitely many real numbers are always bounded. Take some R equal to the max of A1, A2, blah, 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 all the way up to a n minus 1. And take, I don't know, capital D to be the max of M and R. Then for all n, absolute value of AN is less than or equal to D. So the sequence is bounded. So what I did was it converges to something. So eventually all the terms get trapped in here. And there's only finitely many terms on here. So I can just pick a bound for these terms to just be the biggest one that shows up, because there is one of those, because there's only finitely many over there. And then just take the bound on the whole sequence to be the maximum of those two. And that number necessarily bounds both the beginning and the end part, which is the whole thing. Next, we have a few limit laws. If we let AN and BN be some sequences of real numbers that approach some real numbers, A and B, then 1 AN plus BN as a sequence approaches A plus B. 2 C times AN as a sequence approaches C times A. 3 AN over BN as a sequence approaches A over B if the BNs and the B are not 0. and also an times bn as the sequence approaches ab. Okay, I'm going to prove a few of these. I'll leave 3 and 2, how about, as exercises for you, but I'll prove 1 and 4. So we're going to show the addition law first. We can add 2 things together. What we eventually want is that the distance between an plus bn and a plus b, we want that to eventually be less than some arbitrary epsilon we're going to choose. That's if and only if we're going to distribute this minus sign right here. It's going to be if and only if an plus bn minus a minus b is eventually less than epsilon. Do a little bit of commutativity reordering in here. That means an minus a plus bn minus b is less than or epsilon. Okay, we know what this is. Oops. We can bound this because we'll call this A. Eventually, big A, we can use the triangle inequality here. Big A is less than or equal to an minus a, absolute value, plus absolute value, bn minus b. Since an approaches a, eventually this is going to be less than epsilon over 2, and eventually this is going to be less than epsilon over 2. Okay, that's it. So what we're going to do is we're going to say, since first we're going to let epsilon be greater than 0, be arbitrary. Then, since, let's box this off actually. Then, since an approaches a, there is some threshold. Let's call that n sub a. For all n bigger than n, an minus a is less than epsilon over 2. And since bn approaches b, there is similar sum nb, which is natural, such that for all n greater than nb, the distance between the bn's and the b's is less than epsilon over 2. Pick n to be anything at least the max of na or nb. Then the distance between an minus a plus bn minus b is less than or equal to the distance between an minus a plus, we're using the triangle inequality here, plus bn minus b. This thing is less than epsilon over 2. This thing is less than epsilon over 2. So this whole thing is less than epsilon over 2 plus epsilon over 2. That's equal to epsilon. Okay, based on this n right here. Can you get a different color? Yeah, you can even take this to be equals. Yeah, that's fine. Whoops. Okay, so for any n, small n bigger than this big N, this holds. This, of course, is equal to an plus bn minus a plus b. So this thing is eventually less than epsilon. Great. That's what we wanted. Okay, now we're on to the second limit law that I said I'm going to prove, the constant multiplication one. So what we want eventually is that the distance between CAN and CA eventually less than some epsilon. That's if and only if. We're going to pull the C out of here using the distributive property. Okay, then we can break this up. We can pull the C out. That's going to be absolute value C times absolute value AN minus A. And then we're just going to go ahead and divide both of those by absolute value c. So that's going to be an minus a less than epsilon over absolute value c. So we're going to let epsilon be greater than 0. Since an goes to a, there is some natural number such that for every n bigger than big N, the distance between an and a is less than epsilon over magnitude c. Okay, because imagine we choose some epsilon prime to be equal to epsilon over magnitude c. Then there is some n sub epsilon prime such that for all n bigger than n sub epsilon prime, the distance between an and a is less than epsilon prime, but that's equal to epsilon over magnitude c. So we can take the same big N sub epsilon prime that works for this to be the same thing. Okay, then we know that the distance between c times an minus ca, well, that's equal to magnitude c times magnitude an minus a. This thing is less than epsilon over c. So this whole thing is going to be less than epsilon over, should be magnitude c times this magnitude c. All right, we replace this with the epsilon over magnitude c. Maybe it's more helpful if we write it the other way. This whole thing is less than magnitude c times epsilon over magnitude c. And look at that, that's equal to epsilon. So eventually, this thing is less than epsilon, which is exactly what we wanted. Fantastic.